Assalamu alaikum. Here I am Jahangir Alam, lecturer in physics at Milestone College. I welcome you all in my online class. First of all, thanks to Almighty that He has given me the ability to take this class, and I am carrying on my regular activities. Dear students, I also hope all of you are well with your family members. By the mercy of Almighty and carrying on your regular studies, staying at home. Right? In our today's class, we are going to discuss some important topics from the last chapter of physics second paper. That is the chapter of semiconductors and electronics. Right? You know, this is a very important chapter, and today's topics are also very important for your exam. Dear student, mainly today we will discuss on reverse bias, forward bias, p-n junction characteristics, rectification, half-wave bridge rectifier and full-wave bridge rectifier. Right, dear students? I hope you will enjoy it. So, let's start our class. Dear student, before discussing forward bias and reverse bias, we need to discuss p-n junction. You know what p-n junction is. First of all, I would like to say what is semiconductor. Semiconductor is a crystal formed by the tetravalent atom by the covalent bond. So there is no free electron or hole to conduct electricity, right? So to increase the conductivity or the state to conduct electricity, we use some impurities like trivalent atom or pentavalent atom with the pure semiconductor crystal, right? So this process is called doping. That is, the process of mixing impurities with the pure semiconductor is called doping. If we use or if we mix trivalent atom with the pure semiconductor, then this type of doped semiconductor crystal is called p-type semiconductor. On the other hand, if we mix pentavalent atom with the pure semiconductor, then this type of doped semiconductor is called n-type semiconductor, right? So due to the covalent bond in the p-type semiconductor, some holes are created which act like the charge carrier, and in the n-type semiconductor some free electron will be created which will be act like a charge carrier. Okay, so in the p-n junction, if a p-type junction, p-type semiconductor and n-type semiconductor connected by a special process, then this is called p-n junction. In the p-n junction region, you know, the free electron from the n-type semiconductor will diffuse to the whole of the p-type semiconductor. As a result, a certain portion of the junction from the both side of n-type and p-type will be act like a pure semiconductor. Right? So this portion from the both side of the semiconductor will act like a pure semiconductor. So this portion will be known as depletion layer. Right, dear student. So this portion in between p-n junction is called depletion region or depletion layer. Right. So this portion acts as the barrier in conduction of electron or electricity. Dear student, now we will see what forward bias is. You know what p-n junction? If the positive in F of a cell is connected with the p-type semiconductor of a p-n junction and negative end of the cell is connected with the n-type or n end of the p-n junction, then due to the positive or positivity of the cell, the hole in the p-type portion or p-type semiconductor will be repelled and the hole will be created in the depletion layer, right? On the other hand, due to the negativity of the pole, some new electron will be created in the depletion layer. So, dear student, So due to this situation, the depletion layer will be decreased, that is the barrier of the PN junction will be decreased, and in this situation electricity can conduct through this device or through this semiconductor. So this type of junction is called, or this type of connection is called forward bias, right? Due to this biasing, electricity can conduct through this device. Now we will see what reverse bias. If the negative pin of a cell is connected with the p-type semiconductor of a PN junction and positive pin is connected with the n-type semiconductor, then this type of connection, due to this type of connection, that is shown, the negative end of the cell will attract the positivity, or it will provide the electron. So provided electron will fill up the hole in the p-type semiconductor, that is some of the hole will be filled up or balanced by the provided electron of the negative end of the cell. On the other hand, the positive end of the cell will attract the electron. As a result, some electron will be disappeared from the negative end of the PN junction. As a result, depletion layer of the PN junction will be increased, that is the barrier of the junction will be increased. So in that case, the electricity will not be conducted through this device. This type of junction or connection is called reverse bias, right? Dear student, I hope you got it.
Now let's see forward bias. In forward biasing, positive terminal of the battery is connected towards the P region of the PN junction, and the negative terminal of the battery is connected to the N region of this PN junction semiconductor. And you can see the positive terminal repels the holes in the P region, and the negative terminal repels the electrons towards the junction in the N region. So a pressure is acting towards the junction, and this result in the junction to shrink. You can see the junction is shrinking there. Due to this repulsion, the depletion region or the space charge region narrows down, as you can see in the animation. If the voltage in the forward bias is above a specified range, these electrons in the N region drifts through the junction and migrates to the P region, and the holes in the P region drifts through the junction and migrates towards the N region, as like this. You can see the electrons are drifting through the junction towards the P region, and the holes are drifting through the junction towards the N region. Now the current starts to flow across the circuit, and this current is called as the drift current. Now let's see reverse bias. For reverse bias to achieve in PN junction semiconductor, the negative terminal of the battery will be connected towards the P-type semiconductor, and the positive terminal of the battery will be connected towards the N-type semiconductor. So holes get attracted to the negative terminal of the battery. You can see the animation over there, and the electrons get attracted towards the positive terminal of the battery, as per the animation over there. So this result in the increase of the depletion region, the depletion layer, or the space charge region, because you can see the repulsion of the electrons and the holes is happening against the space charge or the depletion layer. So what happens is that this result in the increase of the depletion layer, as see in the animation. That's the depletion layer over there. Now the PN junction act as an insulator and will not allow any current to flow in the circuit. So this junction or this depletion layer now will be acting as an insulator and will not allow the flow of the electrons or holes in that region. But in a particular condition, if the battery voltage is above a particular limit, what happens is that this particular limit is called as reverse bias breakdown voltage. So if the battery achieves this reverse bias breakdown voltage, what happens is that electrons and the holes break down through the PN junction and crosses this junction, resulting in the current to flow through the circuit. So you can see the electrons which are negatively charged crosses this junction, that is breaks through this junction and moves towards the P region, and the holes which are positively charged breaks through this junction and moves towards the N region, resulting in the flow of a current. This breakdown is called as avalanche breakdown. In this process, the current flowing through the PN junction is very high, and ultimately the PN junction gets damaged due to the overheating caused by this excess flow of current. This is how a PN junction semiconductor actually works. So,
Dear student, now we can see some special characteristics for the forward bias. Okay. Inside the junction diode, flow of current is produced by both majority carriers. In forward bias, few milliampere of current is obtained, right? If applied voltage is increased, then flow of current will also increased, and the graph of the current versus applied voltage does not give a straight line, right? This is the main characteristics for the forward biasing. Now we see some special or important characteristics of reverse biasing, and the characteristics are: inside the junction diode, flow of current is produced by the minority carriers, right? In the reverse bias, few microampere. In the forward bias, the current range was milliampere, and in the reverse bias, the range of current was microampere of current is obtained, and no substantial change in the current occurs up to a fixed amount of applied voltage. Okay, we will see a change of current after a certain range of applied voltage. So these are the main characteristics of reverse biasing. Dear student, now we need to see the symbol of a junction diode, that is a PN junction, right? So this is the symbol for the junction diode. This indicates the anode, that is the positive in or P type in of the PN junction is indicates this portion, and this portion indicates, or this in indicates the negative in or N type in. So this point is known as cathode, and this point is known as this point is known as anode, and this point is known as cathode, right? That is the positive pin of the PN junction is indicates by this end, and the negative pin or N type indicates by this end. Okay, so in the circuit diagram we will use this symbol. Dear student, now we will see the characteristic of PN junction. It's a very important topic of this chapter, or related to these topics. Dear student, now we can arrange the circuit for the observation of characteristics of PN junction diode. Here a PN junction or diode is connected like this circuit diagram. A milliampere or ammeter is connected because the amount of current is very small. A voltmeter is connected in this way. RH means rheostat or variable resistance, and E is the source or battery, right? When the junction is connected in forward bias, dear student, this portion indicates the forward biasing. If we hide this portion, then this portion of the graph will represents the characteristics of velocity versus current versus velocity voltage graph for the forward biasing, right? This axis indicates the value of the applied voltage, and this axis indicates the current, that is IF. IF means forward current, right? So for the forward voltage, from the starting, it will not any current, because for the germanium the starting voltage is 0.3, and for the silicon starting voltage is 0.7. So starting from the origin, we will not get any current for a certain value of applied voltage. So after this a certain value, we will get the current. So this value of the applied voltage is known as starting voltage. That is, from this value of the applied voltage, we will get the current in the ammeter, and a certain region will follow the Ohm's law, right? So this portion is known as Ohm's region, because up to this value of applied voltage, the current will be proportional to the applied voltage. Okay, so this portion is known as Ohm's region, and after a certain value, the current will be increased rapidly with the applied voltage, right? And the value of the voltage for which it start or violate the rules of the ohmics law, this voltage is known as knee voltage. That is, after this voltage the value of current increases rapidly with the small change of applied voltage, right. That is shown. This is the characteristics for the forward bias. Now we can see the characteristics for the reverse bias. In the reverse bias you can see for the higher voltage, that is 50 volt, 100 volt, 150 volt, for a higher voltage of applied voltage, the current will be very small. That is, the current obtained in the reverse bias is microampere. That is 1 by 1000 times of the value of current in the forward bias. So after a certain value of the applied voltage, we will get a current which will maintained by the minority charge carrier in the both region, which is known as I naught, and this I naught is known as reverse saturation current, right. So I naught means the reverse saturation current or reverse saturation current. So in this way, after a certain value of the reverse applied voltage, the barrier of the junction diode will be breakdown, and this value of the applied voltage is known as breakdown voltage or Zener voltage. Scientists Zener discovered this phenomena, so this is known as Zener voltage or breakdown voltage, right. So dear student, this is all about the characteristics of curve for the PN junction diode. So you need to practice or study from your textbook at home, okay. Dear student, now we will see the rectification. What is rectification? It is a process. The process by which alternating current is converted into direct current is called rectification, right. In our daily purposes, in many devices we need direct current. Alternating current is not applicable or suitable for the devices. So we need to convert the alternating current to direct current using a special device which is known as bridge rectifier, right. So using semiconductor diode or PN junction diode, we can convert alternating current to direct current. So now we will see a circuit diagram which can convert direct alternating current to direct current, and which is known as bridge rectifier, right. Okay, dear student, now we will see the circuit diagram and graph for the full wave bridge rectification. Suppose there is a AC source, this is alternating current, but we need to convert the alternating current into direct current for our different type of purposes. Here two induction coils are connected. So due to the induction, the current is transferred to this circuit. There is shown when the point M become positive in, then the point N become negative in. So due to the positive or with respect to this aspect, diode D1 will be forward bias, because when it will be positive in, so with respect to this end, so diode D1 will be forward biased and D4 will be reverse biased. So it will be inactive and diode D1 will be active. And with respect to negative end, diode D2 will be reverse bias and diode D3 will be forward bias, right. So for this case, so current will, since this is a positive end, the current will pass through the D1 and then D2 will be reverse bias, so it will be inactive. So current will pass through D1, then load resistance, then B, then follow this path, it will pass through the D3, because in that case, first case, for the positive end at M and negative end at N, D1 and D3 will be active. So current will pass through D1, then load resistance, then following this path it will pass through D3 to the negative end, right, which is represented in the graph. Dear student, this indicates the input circuit, that is the alternating current. But due to the positive half cycle with respect to M and N, this portion, that is half portion of the or half cycle of the full wave will be passed through the load resistance in this direction. So dear student, for the half positive cycle, the current will pass through the load resistance from A to B direction, okay. When the point M will be negative and point N will be positive, that is next half cycle, that is for the next half cycle. Then with respect to the negative, diode D1 will be reverse bias and diode D4 will be forward bias, and on the other hand, when the point N will be positive, then diode D2 will be forward bias and D3 will be reverse bias, right, dear student? So in that case, the current will pass from this point following through F, it will pass through D2, then D2 will be in reverse forward bias. So current will pass through D2 and following the point A, it will pass through the same direction. That is, for the half cycle, the current will pass from A to B, and for the second half cycle, the current will pass through from A to B. Following the point, it will pass through D4 and reach to the negative point. Okay. So dear student, which is represented in the third line or graph, third line of the graph, that is output of the D2 and D4. That is, when the N point is positive and M point is negative, then diode D2 and D4 will be active and D3 and D1 will be inactive. So this is the output of the diode D2 and D4, that is for the negative half cycle. So overall, the total output of this circle was like this, right? So this is the full wave bridge rectification, right, dear student? I hope you got it. Dear student, now we can see an animation of the bridge rectification which will help us a lot to realize this phenomena. Okay.
The circuit used for this conversion purpose is known as rectifier. One of the type of rectifier is known as full wave bridge rectifier. Here, full wave means the rectification, that is, conversion of AC to DC happens in both positive and negative cycle. And the circuit used for this purpose is similar to Wheatstone bridge. That's why this configuration of rectifier is known as full wave bridge rectifier. It consists of an AC supply, a transformer to change the level of voltage, 4 diodes named as D1, D2, D3, D4, and a DC electric load, which could be an electronic device which runs on DC, a DC motor or an electric bulb. Now let's understand the working. When AC supply is switched on, the alternating voltage VAB appears across the primary winding of the transformer. This high voltage VAB is reduced to the level which is suitable for the diodes and the load at secondary winding, and this voltage at the terminals of secondary winding. Let's represent it by VCD. When this alternating voltage VCD is applied across the bridge configuration and the DC load, then what will happen? During positive half cycle, the terminal C becomes positive and the terminal D is negative. Under this condition, the diodes D2 and D4 is forward biased, which we can see here. The anodes of both the diodes are at higher potential with respect to cathodes, whereas diode D1 and D3 are reversed biased. As a result, the diodes D2 and D4 behave like closed switches. Therefore, current flows through the load through this path during positive half cycle in the direction A to B. This current varies in magnitude as shown here. In this way, the positive half cycle of output voltage V0 is equal to IRL appears across the load, where RL represents the electric resistance of the load. During negative half cycle, the terminal C is negative and D becomes positive, thus D1, D3 are forward biased and D2, D4 are reversed. Now current follow this path and it means again from A to B. Therefore, during both part of the cycle, current through load flow in same direction, that is from A to B. This process will continue until any one of the source and load gets disconnected. In this way, the given bidirectional alternating current gets converted into unidirectional DC. Hope this presentation gives you a little bit idea about how full bridge rectifier works. We will discuss.
Right, dear student, I hope you got it or you enjoyed today's class. So thank you very much being with me in my class. May Allah bless all of you. Assalamu alaikum.